Okay, so phase changes. And we're going to talk about the three phases we experience here on the surface of the Earth. Not the most common phase of matter in the universe, which is plasma. But we don't want to be around plasma because that means you're either in a place that's really empty, like space, or someplace that's really hot, like a fire. So we don't want to experience plasma very often. So, all right, first, familiar stuff. What is the term for a solid changing into a liquid? The scientific term for that is melting. The change from a liquid to a gas. Evaporation is one kind, but that's not the only kind. We could also boil it, right? That would be turning a liquid into a gas, and that's not evaporating. What the two have in common is that they're vaporizing. So it's vaporization. So both evaporating and boiling are vaporization. The opposite, what do you call turning a gas into a liquid? Yeah, what do you call it on the outside of your cup? The water that shows up? Condensation. The water on the outside of your cup is called condensation. Okay. And a liquid to a solid is freezing. Anything earth-shattering about those names? The tough one is vaporization because you want to use either evaporate or boil, but vaporization is the... Okay, but these are not the only options. Okay, have you ever noticed, I know I noticed, that if you put water in your ice cube trays and put it in your freezer and leave that ice cube tray alone for a month, when you come back, that ice cube tray will be empty. It will. Okay? The ice cube tray will be empty. The ice will have just disappeared. And it won't have ever melted. It will have gone straight from a solid to a gas. And that's called sublimation. Why does it do that? Well, because remember, everything's moving. And in the freezer, they set up the situation so that if a water molecule vibrates hard enough on that surface and it breaks away, it's got an airflow that pulls that air out so that water can't go back on the ice cube. So anything that breaks away gets pulled out of your refrigerator. So that over time, it goes away and your ice cube trays are empty. All you got is that little white stain from all the minerals in your water. Okay. You can also go straight from a gas to a solid. I mean, because think about it. Frost on a car. Does it look like little frozen drops? Looks like little crystals, doesn't it? That's because it was never a liquid. It went straight from gas to solid. Because if it had been a liquid, we get frozen drops on our car. That's not what we get. We get little crystals. And the name for turning from a solid to a gas to a solid is condensation. And the reason why they use the same word for both is because what does it mean to condense something? What does it mean to condense something? Condense means to make smaller, right? Think about how much space a gas takes up compared to a liquid or solid. A mole of water is 18 grams, which is 18 milliliters. That's if it's a liquid. As a gas, it's 22.4 liters, over 1,000 times bigger. So by turning that gas into a liquid or a solid, I am making it smaller. I am condensing it. Okay. Now, think about the bellwork question. Melting ice, endo or exothermic? Okay. We're taking the ice's point of view. From the ice's point of view, to melt ice, do you have to put heat into the ice or do you get heat out of the ice? You have to put heat into the ice, so that makes melting ice endothermic, right? Okay, freezing water. Endo or exothermic. You never had that happen in your hand, have you? That's not going to happen in your hand. So how am I supposed to know? Well, the answer is because you know the answer to the first one. If I have to put heat in to melt the ice, then I'm going to get heat out when I form it. And that's why the back of the refrigerator gets hot. It's taking the heat out of the ice cubes and pumping it into the room. Okay? So everything going that way is endothermic. To melt something, I got to put heat in. To vaporize something, I got to put heat in. To sublime something, you have to put heat in. Everything going the other way is exothermic. Because this way is all about, this way is all about breaking bonds or breaking attractions, breaking them apart. And breaking things apart always takes energy. And this is about making bonds or making things stick to each other. And making things always releases energy. Making bonds releases energy, breaking bonds takes energy every time. So anytime I stick them together, I'm going to get heat out. Anytime I tear them apart, I'm going to have to put heat in. And that's why our decomposition reactions tend to be endothermic, but our combination reactions tend to be exothermic. And so that's the energy. There's also temperature tied to phase change. Okay? And this is the important part. The temperature doesn't change during a phase change. So, whatever phase change you're going through, you heat something up until it starts to melt. While it's melting, its temperature doesn't change. The energy goes into tearing it apart, not making it move more. And then, once it gets all torn apart, then it can change its temperature and make it move more. Okay? So if you've got a mixture of ice and water, the temperature is 0 degrees. That's why they picked 0 degrees Celsius for STP, because you don't even need a thermometer. And that mixture of ice and water is going to stay at 0 until all the ice melts, or all the water freezes. No matter which direction, the temperature is going to be 0 degrees. So until it's all melted or until it's all frozen, it's going to stay at 0. Once I freeze it all, then I can drop it below 0. Once I melt it all, then I can get it above 0. But it's going to stay at 0 the whole time it's melting. And same thing for boiling water. At 1 atmosphere, boiling water is 100 degrees Celsius. And we're at about 1 atmosphere pressure here. Varies a little bit day by day. Sometimes we're under high pressure, sometimes we're under low. On Monday, a low pressure system is coming, and we will have a chance at rain. And you can't get the temperature any higher until it all boils away. Now, if the pressure is not 1 atmosphere, the boiling point's a little different. Because if you think about what boiling is, to boil something, you have to make a bubble underwater. Got to make bubbles, right? And to make bubbles, you have to lift the water. But the outside pressure is pushing on the water. So in order to make a bubble, you have to lift the water, which means you have to push the atmosphere out of the way. So the less pressure there is, the easier it is to make a bubble, which means that it'll happen at a lower temperature. So that's why if you pick up a box of food you're going to cook and they have the instructions on it, they usually have 3 sets of instructions. First, stovetop, then microwave, then high altitude. High altitude because the higher you are, if you live in Big Bear, you've got less air on top of you. There's less pressure. It's easier to make a bubble. The water's going to boil at a lower temperature. So the water you're cooking with isn't as hot. So everything has to cook longer. The higher you go, the lower that boiling point gets to, until you get to the mountain climbers. As they go high enough, like if you're climbing Mount Everest, you reach a certain height and you have to stop eating cooked food. Because you can't get the water hot enough to kill germs. Because it boils before it gets hot enough to kill germs. And one of the reasons we cook our food is so that the living things don't continue to live inside us. Right? So they have to go to prepared foods because they can't get the water hot enough to kill germs. Because it boils too easy, because there's not enough pressure holding those bubbles in. And you can't get it above the boiling point until it's all turned into a gas. So if that boiling point's lower, that water's always going to be cold. Okay, now energy. So we're going to have names for the energy. And the names are, there's 4 of them and 3 of them are really descriptive. One of them is called the heat of vaporization. And since vaporization is turning a liquid into a gas, it's the heat to turn a liquid into a gas. But it's specific about how much liquid. One gram. How much heat to turn a gram of liquid into a gram of gas? How much heat to boil it, or how much heat when it evaporates? Closely related to the heat of vaporization is the heat of condensation. Now with condensation, they could have picked either all the way to a solid or just to the liquid. They went to the just to the liquid. Again, for 1 gram. The heat of condensation is when 1 gram condenses. The energy when 1 gram condenses. The heat of vaporization is when 1 gram vaporizes. Names make sense? Now, these two heat, for a substance, these 2 heats should be related to each other. Because if I have to put energy in to boil it, I get that energy back when it condenses. That's why we steam our vegetables. Boil the water, and then the steam condenses on the vegetables and gives it all the heat that went into boiling that water. It's the same amount of heat, and actually for water, it's a pretty big number. Every substance has their own number, and water is big at 540 calories per gram. That's more heat than you got out of your the guys did that reaction with peroxide the other day. Nobody got 540 calories. You all got less than that. You should have gotten around in the 2200 range in terms of how much it changed, but you didn't get this much heat. Okay? It's a big number. And it's a big number, so this right here, seems strange, it's why we sweat. Because every gram of water that evaporates off our body takes 540 calories with it. So we sweat as a cooling mechanism. Get warm, our body covers us, pumps water to the surface, that water evaporates, cooling us off. Because 95 degrees here is different than 95 degrees in Louisiana. Because in Louisiana it's 95 and humid, and the water doesn't evaporate. So you sweat and get hot, and it doesn't cool you off. And it doesn't drain, and it doesn't evaporate, so you're wet and hot. Because it can't evaporate, it doesn't cool you off, so it doesn't do you any good. That's why you're uncomfortable when it's muggy. It's because your water's not evaporating. That's why you got to stay hydrated, because if you can't evaporate, you can't control your temperature. And you overheat. Once you hit about 104, brain cells start to pop. Not a good thing. Okay? Now, have you heard the phrase sweat like a pig? That means you're not sweating at all. Because pigs can't sweat. Okay? But that's why you always see pictures of pigs wallowing in mud, because they want to cool off. So they cover their bodies with water by rolling around in it. And when it evaporates, it's cooler. It's why every time you step out of the pool, no matter what the temperature is, you feel cooler. Because that water on your body is evaporating. Okay? It plays a big role in that regulation. Dogs can't sweat on the pads of their feet. That's why they pant. Okay? Most animals cool themselves off by panting. We're bizarre in that we cover ourselves with water. And that's why humans could hunt gazelles with spears. Because gazelles have to cool off by panting. But they can't run and pant at the same time. Humans can. Humans can cool off while they're running. So they wouldn't try to chase and catch the gazelle. They would run just to keep the gazelle running. And if they kept it running long enough, it would overheat and fall down and die of heat exhaustion. They were exhaustion hunters. Because it would just the gazelle couldn't cool down, its brain cells started dying. So that's how humans caught gazelles. So they just exhausted them, overheated them. All because they couldn't get rid of that heat of vaporization. So stay hydrated. Okay. Now the other phase changes have names, and this next one, I didn't get to pick the name because it is wrong in so many ways. Okay, heat of fusion. When we studied fusion as to what was happening in the nucleus when two nucleuses came together and two hydrogens turned into a helium. This is not what's happening. In fact, the opposite of two things coming together is what's happening. Heat of fusion is the heat to melt it, to take the solid and break those pieces away so they can move around. So this one's the one that's named wrong, but I didn't get to pick the name. And since they label it as heat of fusion on the back of your periodic table, that's what I got to call it. But that's what everybody calls it too. The opposite change gets the name you'd expect. Heat of solidification. And think about the bell work today. One of these is exothermic, one of them is endothermic. Heat of fusion is endothermic, heat of solidification is exothermic. When ice forms in your freezer, you have to take the heat out of the ice and pump it outside of the freezer. That's why the back of the freezer gets hot. That's what all those coils are doing on the back of the freezer, is to get rid of that extra heat, let it radiate. Because what they do, this is how a freezer works, is they pump a liquid into the freezer. Inside the freezer, that liquid absorbs heat and boils. So it boils and turns into a gas inside the freezer. That gas leaves the freezer and runs to the compressor, which pressurizes it enough to turn it back into a liquid, but now it's a hot liquid. Then that hot liquid runs to the coils to get rid of the heat before they pump the liquid back into the freezer so it can boil again. That's why your air conditioner has two separate units. It's got an inside and an outside. Inside, the stuff's boiling. They pump that gas outside to that big unit. That big unit out there is a compressor that squeezes that gas back to a liquid and gets rid of the heat. You can see the coils all inside the box and pumps the liquid back into your house. So it's usually freezing and boiling in different places, or boiling and condensing in different places to cool off. It boils inside the house, it condenses outside the house. It boils inside the freezer, it condenses outside the freezer. So now, for water, it's 80 calories per gram either way. Because they got to be the same number. Because otherwise, I could freeze and melt water and generate energy for nothing. And that doesn't happen. I can't get energy for nothing. I can't create or destroy energy. And 80 calories is a pretty big number. Hey, so next I'm going to show you a graph. And this graph is called the heating curve. And what it's a graph of is temperature versus heat. So I'm starting right here. I've got a substance, I've got 1 gram of substance, and it's at negative 20 degrees Celsius, and I start heating it. This substance is water, and at negative 20, water's ice. So I start heating it at negative 20. Ice doesn't melt until it gets to 0. So I'm going to have to heat it up to 0, and I will get a temperature change with that heat until I get to 0. And at 0, the temperature stops changing. Because at 0, the ice is melting. And the temperature doesn't change during a phase change. Once I've melted it all, then it's water, and I can start heating it up. So that big long line is about the fact that you're heating up the water. Then I can heat water all the way up to 100, and then it's going to start to boil. And it's going to stay at 100 the whole time it's boiling. And once I get it all boiled, then I can hit the steam above 100. Okay? So see how what's happened here? This is just what happens to the temperature when you heat water. There's a couple of flat spaces, and those flat spaces are where it doesn't change. The temperature doesn't change because it's a phase change. So that line, that long flat line right there, that represents the heat of vaporization because it goes from 220 to 760. That's 540 calories apart. That's why that line is that long, is because it takes that much heat to boil a gram of water. This one goes from 40 to 20, 80 calories apart. That's how much heat it takes to melt water. Right? And these other ones, it's got a slope, right? And the slope would be y, temperature, over x, heat, change in temperature over change in heat, which is the exact inverse of specific heat. So that's the slope of that line is tied to specific heat, but it's actually inverse. Because if you think about slope, it's temperature over heat, and specific heat is heat over temperature, calories over degrees Celsius. That's the inverse. But between 0 and 20, I have all ice. Negative 20 and 0, I have all ice. Between 0 and 100, I have all water. And above 100, I have steam. And at 100, I have both water and steam. On the left-hand side, it's all water. On the right-hand side, it's all steam. Any place in between, it's both. And at 0, I have a mixture of ice and water. Left-hand side, it's all ice. Put in some heat, it'll turn into water. Once it's all water, then the temperature can go up. So on those flat lines, I've got a phase change happening. Okay? Every substance has a heating curve where these lines are different lengths for the heats of vaporization and heats of fusion, and the slopes are different for specific heats. Because you can see that the slopes differ on my 3 lines, right? That's because water, ice, and steam have different specific heats. Okay. So tonight's homework is going to have you calculate some energies. And we have 3 equations to worry about. And we use them at different times. One of them we already know. When there's a temperature change, heat equals mass times specific heat times change in temperature, which we wrote as Q equals mc delta T. So anytime we were in one of those places where it was changing temperature, I can use that equation. This equation won't work for phase changes because with phase changes, the temperature change is 0. So if you put change in temperature in the equation, you'll get 0 every time. And we know it takes heat to melt ice. Okay, when there's a phase change, you have to decide which one it is. If it's melting or freezing, we can do heat equals heat of fusion times the mass. Q is heat. Heat of fusion, we write delta H, and then we write FUS as a subscript, heat of fusion, times the mass, M. For water, I will use this every time it's at 0 degrees Celsius, and it's not changing temperature, either freezing or melting. Okay, and heat of vaporization, heat equals heat of vaporization times the mass. Or Q equals delta H vape times the mass. So what do I do if I heat it up and both the temperature and the phase change? The answer is do them separately and add them together. Figure out how much heat to change the temperature. Figure out how much heat to change the phase. Energy is conserved, so you can add them together. And that's how much heat it's going to take to do both. Because if you think about what happens to an ice cube when you drop it in your drink, if you just drop an ice cube into your drink and then walk away, first thing that's going to happen is that ice cube is going to melt, and that's all going to happen at 0 degrees Celsius. And then once it's all melted, it's going to warm up to room temperature. Right? You don't have to go complex to see both are going to happen. It happens all the time. But because energy is conserved, you can do them separately and add them up. Okay? That's it. So all you have to decide is it a phase change, a temperature change, or both? Okay. Do them separately and add them up. So how to do it? Total heat equals the sum of all the heats you have to use. You get to add them up. So what I do is I go in order. I ask myself, what is going to happen when I heat this? Is it going to change phase or is it going to change temperature? The first bit of heat, what's the first bit of heat going to do to it? Is it going to change temperature because it's not at a melting or boiling point? Or is it going to change phase because you're at the melting or boiling point? So this is the order it goes. If you start at 0, first you're going to melt the ice. Then you're going to be able to heat the water. And then then you can boil the water. So talking about an ice cube I drop into a drink, first I'd melt the ice, then I'll heat the water up to 25 degrees Celsius, so I'd have to do 2 equations and add them up. And the numbers I need for water, fusion's 80 calories per gram. And see how I've got a temperature change, so my number has a temperature in it. 1 calorie per gram degree Celsius. Can you see why chemists like calories better than joules? Because all those numbers would be 4.18 times bigger. On the homework tonight, some of them I ask you to do some of them in joules, but I give you these numbers in joules. You don't have to memorize these numbers. They're printed on the back of your periodic table. I didn't have to do it. State decided that's things you should know, have access to. So ask yourself what's going to happen to it, and it'll let you pick what equation. It's either going to change phase, or it's going to change temperature. Or it's going to do both, and you do them one at a time. So how much heat to melt 12 grams of ice at 0 degrees Celsius? So I've got ice at 0 degrees Celsius. What's the first thing that's going to happen to ice at 0 degrees Celsius when I heat it? Is it going to change temperature or change phase? At 0 degrees is where it melts, right? It's at the temperature to melt, so if I put heat in, it's going to change phase. Is it going to change temperature? No, they want to stay at 0, so I'm only going to have to do one here. This one's just going to change phase, and the phase is melting, so it's Q equals heat of fusion times the mass. And the heat of fusion is 80 calories per gram. And the mass was 12 grams. So it's going to be 960. The grams cancel out, and I get calories. So just pick the right equation. It's not the math that's going to trick you up. It's picking the wrong equation. Think about what's going to happen. Compare that to this question. It looks almost the same. How much heat does it take to heat 12 grams of ice at 0 degrees Celsius to 25 degrees Celsius water? So, I got that 12 grams of ice at 0 degrees. That's where I'm starting. I put heat in. What is that heat going to do to my ice cube? Well, the first thing it's going to do is melt it, right? And then once it's melted, then I can heat it to 25. So I'm going to have to melt the ice, and I'm going to have to heat the water. The melted ice one is the same as it was last time. Q equals heat of fusion times the mass, which was 12 grams, was 80 calories per gram, times 12 grams. That was 960 calories. And that gets me water at 0 degrees. I haven't changed the temperature yet. So now I need a temperature change. So the second one is going to be Q equals MC delta T, because the water is going to change temperature. The mass of the water was 12 grams. C is 1 calorie per gram degrees Celsius. The change in temperature is 25 degrees Celsius. So 12 times 25 is 300 calories, because the degrees Celsius cancels and the grams cancel. So the amount of heat it's going to take is 1,260 calories. Notice most of that energy went into melting the ice cube. About less than 1/4 of it went into heating the water up. And that's why we put ice in our drinks and not cold water in our drinks. Cold water wouldn't change the temperature enough. Put ice in because it takes a lot of energy out of that drink to melt that ice cube. Whereas if you just put cold water inside, that's why when you're trying to put ice, when you put cold on an injury, you don't put water on an injury, you put ice, so it stays cold a long time. I mean, you can put cold water, it just doesn't last. Okay. How much heat does it take to heat 35 grams of water at 0 degrees Celsius to steam at 100 degrees Celsius? Now, looking at this, I'm starting off with water at 0 degrees Celsius. What's the first thing that's going to happen when I try to heat that water at 0 degrees Celsius? Is it going to change phase or is it going to change temperature? It's going to change temperature, right? So I don't have to do the melt the ice part because it's not ice. I do need to heat the water. I could heat it to 0, but then I want steam, so I'm going to have to boil it too. So I need to heat the water and then boil it, right? So the first one, Q equals mc delta T. The water is going to change temperature first. It's going to start off as 35 grams times 1 calorie per gram degrees Celsius times change in temperature from 0 to 100 is 100 degrees Celsius. So that's 3,500 calories. I don't need a calculator because 35 times 100 is 3,500. And the grams and the degrees Celsius cancel out, which is why I'm left with calories. Then I'm going to boil the water, which is 540 calories per gram, which is the heat of vaporization times the mass, which is 540 calories per gram times 35 grams. And that one I can't do in my head very well. So 35 times 40 is 18,900 calories. So my total amount is going to be 22,400 calories. Notice how much of the energy went into boiling the water. 19,000 out of 22,000. It takes a lot of energy to boil water. Okay? So those are the kinds of problems you're going to practice on here. Okay? I've got all the numbers you need up top. I put it in both calories and joules. So let's see if they match up the units. They ask you for joules, use the one in joules. They ask you for calories, do the one in calories. If they give you calories, use the one with calories. If they give you joules, use the one with joules. Make the units work. Okay. For the first 9 of them, I've done 2 things. For the first 9 of them, I've given you the answers. They're in parentheses. And the first 9 of them tend to be one-steppers, so you get used to doing the one-steps. Then you, actually, the first 8 are one-steppers. Because on number 8, it asks you how to melt the ice, heat the melted water, and then boil the water. On number 9, it just says ice at 0 to steam at 100. It expects you to do all those steps. So after number 8, you may do multiple steps, or you might have different heats of fusion. Okay? I would maybe remind myself where it says heat capacity, and I gave you 1 calorie. I might write 0 to 100 next to that to know that that's where it works between 0 and 100. Heat of fusion, I would write 0 degrees Celsius next to that because that's when you use it. When it's at 0, you use that. And I might write 100 degrees Celsius next to heat of vaporization because that's when I'm going to use that one along the way. Math's not hard. Okay? Figure out what's happening. It'll pick the equation for you. Yeah. Well, think about the names. Well, first of all, there's no difference in the equations. Okay, there's only two equations here. There's ones with a temperature change, and there's ones without a temperature change. And if it's not a temperature change, it's a phase change. Okay? So you either change phase or you change temperature. You can't do both at the same time. That make sense? Top one is, so the top one is the temperature change, and it's at between 0 and 100. So melting ice is at 0, so it doesn't have temperature in the equation because the temperature change is 0. This one has 100 degrees Celsius. It's at 100, temperature change is 0, so I don't want temperature in my equation. So it's going to be mass times some number, and every once in a while a change in temperature. If your unit has a temperature in it, you're probably going to have a change in temperature. But it really helps to think about what's happening to the water or whatever you're heating. Is it going to change phase or is it going to change temperature? If you're not at a melting point or a boiling point, it's going to change temperature. If you are, it could either change temperature or change phase. Because water at 0 changes temperature, ice at 0 changes phase. Have a good one.